Welcome to Zen of Concrete Structure course. So this is lecture number 18. So up to this lecture number 17, we have discussed all the basic parts of RCC structural design. So if you recall, just at the beginning, we started with the different building materials which are useful for the design of structures or construction of structures. We discussed in details about different properties of concrete and in details of properties of the steels, and then we have discussed about the characteristic strength of concrete, steel, then all the initial basic parts we have discussed in the early lecture. Then we discussed in details about different types of loads which is acting on a structure, and then gradually we started designing our first element of a structure, that is beam member. So once we designed beam member, next we discussed about the slab design, and then lastly in the last few lectures we discussed about how to design the column member. So essentially what we did is we designed the three basic element of RCC design. So first one is obviously beam, and then slab, and then column. So if you see, what is the major difference in all the structural components whatever we have designed till now? So beam is actually a member where the loads are acting on a transverse direction. So in a beam, the loads are always acting, or you can consider it any structural member where the loads are acting in a transverse direction. That design will follow a beam design. So whatever we have designed beam, so it will follow exactly the beam design. Now, if a structural member is very thin and moderate amount of loads are acting on it, then how to design that? That comes to be slab design. And if a structural member is subjected to a compression force or axial compression force, in that case, that element of a is design will follow column design. So essentially, we just understood the different letters of structural analysis. For example, if you want to learn English, what you have to do? First, you have to understand A, B, C, D, right? All the letters first you have to understand it. Then once you know the letter, then you can form the words. So words are nothing but the individual letters. If you add letters in a some sequential manner, basically you will get the words. Again, if you put multiple words together, you get the entire sentence, right? So this A, B, C, D or the letters are actually basic element of English, right? Similarly, for our structural design also, this beam, slab and column. So these three are basically basic letters of RCC design. So now if you once you understand these three concepts, or beam design, slab design and column design, then you can design any structure in the world. How? If you consider any structure that can be decomposed into beams, slabs and columns. For example, you are designing a bridge, so bridge will be something like that. You will find, maybe if it is a cable stayed bridge, something cable will be there. So this is a cable stayed bridge, right? Or maybe you can consider any types of bridges. So in that case, what will happen? So it is made up of, so this middle member is subjected to slab, right? So this deck of this bridge can be designed as a slab. Then you have the beams all around, so that beam design will come under this one, and then you have the columns also, right? Column design will be followed. So like that, in any structure in the world, you can divide it into a beam, slab or a column, depending on how the loads are acting, what is the shape of the member. Based on these criteria, you can divide any of these three, and then you can design it, right? Beam design we know individually, slab design we know individually, and then in column design also we know. So that's all. So if you know the basic element design of RCC structure, then we can design any structure. We have to simply decompose the structures into these three elements, and then we have to design it individual members, right? So in the lecture number 18, we have started a new topic today, that is staircase design. So staircase is very much important part in a building, which gives the access to go, to move from one floor to another floor, or if you want to go visit to the roof of a structure or a building, you have to use the staircase. So staircase is a very much important structure, important element in a structure or in a building. So today we'll be looking into how we can design a staircase and what are the different key aspects of designing the staircases. Again, as I mentioned, once you know beam design, slab design and column design, the staircase and any other structural design is very simple. So first we have to divide the staircase into these three elements, depending on how loads are acting, depending on how we design. So depending on several parameters, we can simply classify the staircase into these three parts. So let's see first initially what is the different types of staircase which are available. So we call it flight. So basically staircase is basically used to navigate from one floor to another floor, right? Basically the elevation change will be there. So from first floor we are going to second floor, from ground floor we are going to first floor, right? So elevations are changing. So if you imagine, so this is actually the ground floor, then this portion will be the first floor, right? And these are the stairs. So it's simply you are going up through these stairs. So this we call it actually flight. Okay, this one flight means what? We are going up, right? So that's what this is called single flight staircase. Means this is first floor and directly you have a very long staircase and you reach to first floor. So that is the single flight staircase. In many, like if you visit the shopping malls and all, right, or in the airports, you will find the escalator, right? That escalator is basically the single flight staircase because it directly gives from one floor to another floor directly, right? So it is single flight staircase. Now you have two flight staircase, like in many residential structures you will find this two flight staircase, whereas half of the elevation or half of your height you will be reaching in one staircase, and then you have a portion slab portion, and then again you go remaining half. So this is your first floor, ground floor, and then you go to middle of the first floor, and then you reach to first floor. So like that, this type of staircase we call it two flight staircase, because you understand here two flights are there. So this is single flight, this is double flight or two flight. Then we have open well staircase. Like in our if at a campus, all the staircases you can see are actually open well staircase. Means you will have to go one third, you will go up, then again remaining middle one third will go in this direction, and last one third you will go in this direction, and you will reach to the first floor from ground floor. So here is ground floor, then like that you went to first floor. So it is open well staircase. Means if you see, this is a well, right? Inside middle some well type things will be there, so that's why it is called open well staircase. Then next type of staircase is actually helicoidal staircase. Helicoidal staircase. So here you will see there will be a column at this point, and gradually through helical pattern you will be simply go up. Okay, so here basically, this type of helical staircase you will find in many buildings where we have aesthetically looking good. That time we use this helicoidal staircase. Then we have the spiral staircase, means at the middle you have the some center pole and all, and the stair will be simply rotating and it will go up. So when you have very less space for the stairs, then you can go with spiral design because it takes minimum space for the stair. Okay, but again the comfortability in spiral staircase won't be that much as we have two flight staircase or single flight staircase. Okay, so these are the different five types of staircase which we see in our day-to-day life, and each types has advantages and problems as well. So depending on the area, depending on our requirement, depending on the aesthetics, depending on architectural design also, depending on loads, we classify we choose which type of staircase we have to design in our structure. So these are the total five types as we discussed. So now let's investigate a typical flight. Now in the flight itself, what are the different elements are there, that now we'll investigate here. So as I mentioned in the last slide also, there are basically five types of staircases, but here I will be discussing a single flight staircase. If you see the staircase, this is a plan view. So you have ground floor here and you have staircase and you reach to first floor. Okay, so this portion, this slab portion, we call it landing, and landing is there in the both the directions. So this portion at the ground floor we call it landing, and the first floor where you reached, that is also we call landing, and in the middle portion we call it going. So basically this entire portion is classified into two parts. One is two landing in both the ends, and in the middle you have the going means basically you're going up, right? So or going down, whichever it means. So middle portion we call it going, and then we have the landings. Okay, then this is the width of your slab, so it is actually double staircase is mentioned, right? Then these are the different key parameters you will find in a staircase. So first we understood now what is going means the middle portion where basically you are climbing the stairs, so that portion we call it going. And the bottom portion from where stairs starts, that is landing, and top portion where stairs ends, that we call it one more landing. The two landings are there, and middle is going. Okay, so now going you understood. Now let's understand what is thread. So thread means, so each stair will have some width, right? So this width, so you can see if you see the cross sectional view here, so this is the landing part, basically this landing part, and then you have the stair started. So this portion, horizontal portion, we call it thread. So you can see this is the thread we call it. So many threads will be there, 5 thread, 10 thread, normally 20 thread, or maximum if you are using single staircase, then maximum maybe 20 thread is sufficient to reach from first floor to second floor. Okay, so that is we call it thread. And this height of a staircase we call it riser. So this riser we denote it r. The riser is what is the typical height. So normally it is 15 say 15 mm, or sorry 15 centimeter, typically the height of the riser, 15 to 20, depending on if you are designing a residential building, then the riser height may be 20 mm maximum you can give. Whereas if you design a school or a educational building or a hospital building or a big structures, in that case where the more people are going up and down, in that case the riser may be 15 mm as 15 centimeter as well. So depending on again which type of structures we are designing, we can choose what is the thread, I mean what could be the typical thread, what could be the typical rise of a staircase. Then we have waist. What is waist? Waist is this total slab will be there, right? So this is a landing. So if you see, this is one landing and this is another landing, right? So we have at the bottom we have the slab. So this slab basically waist slab we call it. So this bottom portion of the slab we call it waist slab, and this is our D. And then last terminology we'll find in the slab design, it's called nosing. What is nosing? Nosing is basically we sometimes give some portion extra, right? Some projection will be there. So for example, if I draw here a steps, so like that steps are there, right? That is schematic diagram, but in reality if you see, some steps will be something like that. So some extra projection we keep it in a slab, right? So this portion is actually called nosing. Okay, this is the nose of a stair. So every steps you have small projection you will be finding, so that portion we call it actually nosing. So these are the different five different terminologies we will be extensively using in the staircase design. So, and this is another type of slab. If you see, all the stairs are actually not connected through a beam. So here if you see that waist beam is there at the bottom, but here in this type of thread riser, so this is we call it waist slab type uh, that stair. And this one, second case, this one is basically we call it thread riser. So directly where the thread and riser is increasing, right? So there is no slab at the bottom. So this is another type of staircase also. And this is our third type of staircase, which is isolated thread slab. So basically these slabs are directly projected from the wall, and these are not connected each other, directly projected cantilever wall, you can imagine. So maybe one side is you have a wall, maybe that side you have a wall. So from wall, this type of small cantilever slabs are coming out, and this makes our mm, that staircase. Okay, so this is isolated thread slab. So these are the different definitions we'll be using in the slab design, in the staircase design. So before starting into our main design part, let's see some general guidelines for designing of staircase. The respective dimensions of the thread and the riser for all parallel steps should be same in consecutive floors of a building, right? For example, you are constructing a five-story building. So whatever dimension of thread and riser we are using in the ground floor, it should be same for all the floors. It is not like one floor you give 15 mm riser, 15 mm, for example, this is a slab, so this is a staircase and this is the riser part, right? So so if you give 15 centimeter riser in ground floor, then in all floors you have to give the same riser and the same dimension as well for thread also. Why? Because see, for example, you are visiting some in a building, big building, right? You are using the staircase. So when you are going from first floor to second floor, you just comfortable with whatever is the riser and thread they have provided. But from the second floor to third floor, whenever you are visiting, that time already in our subconscious mind we have some basic idea that what is the dimension of riser and thread of this building. Now if you change it in the second to third floor, then again it will be very much uncomfortable for the customers to visit that building, right? So that's why the whatever dimensions the riser will be using at the ground floor, that should be same throughout the structure. The minimum vertical headroom above any step should be 2 meters. So whenever one person is standing here, right, then roof will be there. So one person if is standing here, so roof will be there somewhere here. So minimum that gapping should be 2 meters. That you have to ensure, you have to maintain that. So generally the number of risers in a flight should be restricted to 12. So one riser it should be restricted to 12 normally. The minimum width of the stair means if you see from the plan you will see the width of the stair should be 850 mm. These are the approximate general values you will find it. So that's why whenever you design a staircase you can choose 850 or 1 meter width. So depending on which type of structures you are designing, how many people will be coming and down, are going up and down, based on that basically you can choose the thread as well as the riser of a building. So the minimum width of the staircase should be 850. Though it is desirable to have a width between 1.1 to 1.6 meter. In a public building cinema hall, that the large width of the staircase should be provided, because in the public buildings basically more number of people will be visiting. So in that case, the width of the slab also should be high. But for the residential building, maybe for two-story building, the width maybe 850 is also sufficient, because very less people will be staying there, right? So now we'll see what are the different structural systems. As I mentioned, we can divide, or we can disintegrate the staircase into these basic three elements like slab, beams and columns, right? So if you see, this is a typical slab, a schematic diagram of slab. This is a two flight slab, because you have the up first floor, middle you came, this is landar, right? So this is a ground floor landar, you go up, this is middle portion landar, and then you go to first floor. So this is a typical that is two folds, that staircase where you have the cantilever. So this landing is basically cantilever landing, and this middle portion also is a cantilever landing, because this slab is basically restrained from this side of wall, this side of wall, this side of wall, right? This is a cantilever also, you can imagine. So now this staircase can be uh, idealized into different types. What are the different types? So you can imagine that E point, this is this point at the ground floor, this is simply supported, and then you made a cantilever beam. Here you did not provide any support, so you made a cantilever beam. So from cantilever beam you have the slab, that stair slab, and then again at that point again you have the cantilever portion, and then you have the simply supported case here. This is one type you can design. So simply separate case here, and then like that you provide. But if you use this configuration, so what will be the problem? That will be discussed. First, let me complete different support condition, then we'll discuss one by one case. So this is the first case where we have the simply supported case, we can provide it at the both ends. Now this is another configuration you can design it, where the both ends you are clamping, right? This is a fixed support, we are clamping both the ends. So this is maybe another beam you can consider, something like that. So this is one type of beam. You can see how the beams looks like. This is a cantilever, the simply supported beam. And what is the dimension? If you see, this is not uniform. So till now, whatever we designed in the beam design, so our beam was exactly horizontal, right? With a support condition, it may be a cantilever, or it may be simply support, whatever it may be, roller it may be. But now the same beam we are designing, but the dimension here is little changed. Earlier it was straight, but here the beam is not straight, right? Beam is an inclined middle portion and something like that. So you can consider this as a beam, and you can design it simply, very simple. As I mentioned, now we'll be dividing this stair into our beam, column and slab portion, right? So this you can consider it as a simply supported case, or you can consider it as a fixed, and also, or you can consider it as overhanging, like see, this is the overhanging beam, right? So you have one support here, this is another support here, and cantilever portion here, middle portion simply support, and again you have cantilever. So this is overhanging beam you can consider, or you can consider something in that manner, like you have the simply separated case, and then you have two simply separated case here. Or you can design something like that, continuous beams. So this is one beam, another beam, another beam, so continuous beam. So you can classify this staircase into different idealizations. Which one will you take? So now what is the problem? So if you have option with this one and this one, which one will you choose? Either you make it simply support or you make it fixed. So both has advantage and disadvantage also. So in the simply supported case, if you recall, what is the bending moment diagram for the simply supported beam? So so this is a beam, you already have drawn it. So if I draw this bending moment diagram of this beam, so bending moment diagram will be something like that. Okay, so both the ends you have the zero bending moment, here zero bending moment, here zero bending, because these are simply supported supports. So zero bending moment, and this is the positive bending moment at the center of the span. Right, now if you have a fixed support, so now if you have a fixed support at both the ends, then what will be the bending moment diagram? So bending moment diagram will be, you have the negative bending moment at the support, then positive, negative, so something like that. This will be the bending moment diagram for the fixed end side support. So if you use cantilever, that simply supported type support, then what will happen is this bending moment, positive bending moment will be very high. In that case, the depth of the slab will be high compared to this fixed end beam. Why? Because fixed end means you have the negative bending moment near to the support and positive bending moment at the middle. Because of that, the positive bending moment also will be reduced comparative to this one, and you have the small negative bending moment as well. So this will help us in reducing the thickness of the beam. So this beam's depth will be now reduced if you use the fixed end beam. So now we know how to design the continuous beams or fixed end beam or simply separate beam or cantilever, whatever it may be. So that is simple beam design will follow now here, and using beam design, whatever we started earlier, easily we can design this portion at least. Okay, so now if you see the landing part, so this is a landing part, right? So this is a landing part. So landing part is, we normally provide say, a slab type thing. So landing design, you can consider it as a slab design. So one-way slab or two-way slab, depending on the shape of the landing, you can design it. Mostly it is one-way slab design. We can employ slab design, and we can easily draw. We can easily find it out, the slab, the landing portion also. So now that we discussed stair in the longitudinal direction. Now we'll see stair slab spanning in the transverse direction. Means transverse direction, how the slab look like. So this each thread, how to design that. So in the last slide, basically we have seen how to design this climbing part, right? This is a slab part. So now in the slab we have the stair. So these are the stair, right? So now in these slabs or steps also we have to design it. So this is actually transverse staircase. So that's transverse staircase, how it looks like. So if the staircase is embedded on a wall, then something like that small beam you will find it out. Or if it is a cantilever, so one side is on a wall, another side is simply projected. This is the step, one step. So this is simply cantilever beam, you can imagine. Or maybe you provide this middle beam, and from the beam two sides you have the steps, something like that. So that is also another type of transverse slab, stair slab, you can design it. So anyone we can choose depending on our configuration, depending on our availability, we can choose any of these slabs. So now what is the effective span of stair? So we already seen what is effective span for beam, what is, we have already seen effective span for the slab as well, effective depth or effective length for column also. Now here we have effective span for the stair. So if you visit clause number 33 IS 456, it gives what is the effective span of a stair. So three different cases. So first, what you have to do is the horizontal center to center distance of the beams should be considered as the effective span. So for example, effective span in a stair, maybe you have a landing here, up, one more landing, right? So you have beam here, here one more beam, right? So the horizontal beams. So center to center distance of this horizontal beam can be considered as this is effective span. This is our first criteria. When the slab is supported at top and the bottom raised by the beam spanning parallel to the riser. Okay. Now second case, the horizontal distance between the distance equal to the going of the stair plus each side half of the width of the landing or 1 meter. So this is one problem, you can take it. And next category is half of the landing. So you have the landing here, you have landing here. So half of landing also you add it, and whichever is smaller, that stair slips when the stair slab is spanning from one edge to landing slab which is parallel to each other. Okay, so either you can take center to center distance of the beam, or you can take center to center distance plus the half of the landing, or 1 meter, which is very small, and that also can be used as effective span of the stair. So these are the basic guidelines. Now let's see now what one example of how to design a real life staircases. Okay, so now we understand staircase can be divided into a beams and columns and slabs as well. So the main riser portion, or the main bottom portion, we can design it as a beam design, and the landing portion we can design it as a slab design, and obviously all the sides we have the columns also. So let's see an example here. So design a waste slab. So waste slab is given to us. This is a figure landing slab. So we have to design a landing slab A. So we have the landing slab A is this portion which is at the ground floor. You can imagine. Then you go middle of this floor. We have the landing B. Then come here again. You go to first floor. Right. So landing A is supported on a beam along JK. So this landing slab is here, right? So this is landing slab. So landing slab is supported on a two beams. So one beam is at a JK, another beam is at PQ, right? The JK and PQ. While wedge slab and landing slab B are spanning longitudinally as shown in figure. Okay. So the finish load, floor finish and live load is given to us. How much load is applied on this staircase, that is also given 1 kN per meter square and 5 kN per meter square respectively. Use riser. So riser value is given to us 160. What is riser? So riser means this height, right? Height of this each step. So this is our riser. So riser value is given to us 160, and thread is basically, so this one, this length is T. That is also given to us. So which is 270 mm. So concrete grade is given M20, and Fe415 steel we have to use it. Okay, and this is a plan view is given to us, and loads also given to us. We have to design the slab as well as landings also. So slab design will follow something like beam design, whereas landing portion is will be followed by the slab design. Okay, so now let's get started. So now first is design of going and landing slab B that we are doing. Okay, going means this inclined portion, and the landing slab B we are designing. So R value is already given to us. R means rise 160 mm. So if I draw here the slab, you have the landing here, and then you have slab, one more landing, right? So, and in the inclined portion you have this stair. Okay, so in the stair this height is given to us, which is R, and this is thread T. Now what is this inclined portion then? So what is the value of inclined portion? That will be root over of T square by R square, right? From the Pythagoras theorem we can easily write what is this inclined portion. Similarly, what is this inclined portion? All these things we can do it. So that's what we are doing. So inclined length at each step we are now computing. Each step is root square of R square plus T square, which is nothing but 313 mm. So each height inclined length is 313 mm. Okay, so now effective span and depth of the slab. So effective span, if you visit clause number 33.1b and c, there you will find effective span will be total. This inclined portion is basically 2700. It is given in the last slide. If you see, this total slab length is given 2700 plus 750, means half of this landing. So this landing is given to us 1500, so half of this landing, and here it is embedded on a wall, so entire length we will consider, which is 150 is the total landing. Okay, plus 150 is the 150 went inside the wall, so half of this wall also 150 we consider. So total effective span is 5100. So now we got it, total effective length of this beam or the slab is basically 5100. How? So 750, this side landing is given to us 750, 1500, so half we consider it 750. Then this length which is given to us 2700, then this is entire landing 1500 plus half it inside the wall, and all this 150. So now the depth of this slab can be considered as a, so this effective span by depth ratio for the cantilever beam. You can remember what we discussed in the beam design also, for the cantilever beam design or the slab design also, effective depth by span ratio. Sometimes we call it, we assume 20, 25, 30 depending on support conditions, right? So here also effective depth by span ratio is 20, that approximately we consider. So 5100 is the effective length divided by 20 will give you 25255. This is approximately the depth of the slab, depth of this slab we can consider to start with. So let's assume the total depth is 250 approximately, then we'll check it, right? In the other step 2, step 3, we'll check it whether our assumed depth is correct or not. So this is 250 mm, and effective depth will be then 250 minus 20 is the clear cover we are using, and 6 mm diameter also we are reinforcing bar using 12 mm we are using. So 12 minus 2, 12 minus half is 6. So how we got it 6? Let me draw it here, then the portion will be clear to you. So this is the dimension, maybe width. So width of the beam, so total is 250, right? 250. Then we have the clear cover, reinforcements are here. So this clear cover is given to us, we assumed actually 20. And then what is this 6? We subtracted. So in this reinforcement we provided, and as well as in the transverse direction also, right? Like that we provide reinforcement. If you recall in the slab also how we provide reinforcement. One is longitudinal reinforcement, another is transverse reinforcement. So now the effective depth will be half of up to this level. Okay, if the total width of this bar is 12 mm, then half also we have to subtract it. So that's why half minus 6 is subtracted. We assume that we will provide 12 mm reinforcing bar, mean that bar 12 mm reinforcing bar. So depth of the landing slab is assumed to be, so we have the landing also, right? Two sides, that also we have to design it, landing B and landing A. So landing B, let's consider that also depth would be 200 mm, and effective depth again 20 minus 20 clear cover minus 6 is the beam. So this is our assumptions, and initially we just taken. So every designer can take some other values, but values should be reasonable, right? You cannot use the effective depth 1 meter. Okay, so one, if it's that is very unlogical thing, so that's why we normally use 250 or 200, whatever it may be. These are the logical range of assuming the data. So now step 2 is the calculation of loads. So similar thing what we did in the beam design also. First we computed what is the effective length, and then in the next step we do calculation of load. Then in the step 3 what we do the calculation of bending moment and shear force. Then in the step 4 we find out what is the reinforcements required. All the processes or the steps are same even for the slab design as well. So calculation of loads, very simple. Loads on a going means this inclined portion, we call it going, right? On a projected plane area. So self weight of the slab will be 25 is the 25 is what the density of the concrete, reinforced concrete, and the thickness of the slab is 250 mm, so 0.25. And the riser, what is the inclined length? So inclined length is 2380 by 270. 270 is what? Riser, right? 270 is riser, and 313 is the inclined portion. So this by this, so self weight is coming to be 7.2 kilonewton per meter square. Okay, so this is meter square we converted. Now self weight on a steps. So this is on the inclined portion, right? On the slab. So let me draw it here. So you have landing, and then inclined portion, and then one more landing, right? So this is the slab, waste slab, whatever we are considering it, this portion is basically this inclined portion, and then you have now steps. Okay, so this steps load also will be coming into the slab. So the what is the self weight of the step, that is 25 is anyway density, and that riser height is, we know that's 16, that 160 mm. So from here you got it, what is the self weight, which is 2 kilonewton per meter square. Okay, now what is the floor finish given to us in the question? 1 kilometer per meter square, and live load also given to us 5 kilometers. So total load, if you add all, you will get 15.26 kilometer per meter square. The total load factor load means we have to multiply this with 1.5 partial safety factor. We get this is the loads on a going. Loads on a going means this portion, what is the total load. Okay, so now loads on a landing slab. So landing slab A, so we have two landing slabs, right? One is at the bottom side, so we have two landing slabs, so something like that. So this middle portion we call it going, and this is our landing slab A and landing slab B, right? So landing slab A, how much load will be coming? It is approximately, you can choose 50% of the estimated load. So same thing, floor finish and all you add it, here you get the 11, and factor load for the landing B is here. This is also, just total is 11, so multiplied by 1.5, because here, see, slab A is resting on a ground, right? That's why we considered 50% of the estimated load. Whatever load is coming, that we considered half, 0.5, we multiplied it. So that much is the load coming. Whereas this landing B is on a middle of the floor, right? So this entire load will be coming into the beams and columns. So all full load we have to consider it. So here that's why we did not multiply it. 11, entire 11 we considered, plus multiply to 1.5 with the partial vector, and this is a load on a landing B. So now if you see, this is our beam diagram. If you see, so left side is our landing A. So this landing A, this is the landing A part, where the load is how much, 8.25 kilonewton per meter square, and both the supports we consider it as a simple support. So this landing portion we have 8.25 loads are acting. The middle portion, middle of the slab, it is 22.9. Last slide, the step 1 we computed already 22.9, and this portion again we have the full 16.5 here. So this is a beam. Now you can see how we idealized our entire slab into a simple beam with different loading patterns. So now it is essentially a very simple beam design with loads already computed. So now we have to draw the bending moment, find out what is the maximum bending moment, what is the maximum shear force, and the simple beam design will follow it. So now you can see how we have distinguished, or how we have disintegrated the entire slab into a simple beam design with the different loading pattern. So how we idealized, that is very much important to understand. So now already we know the loads. Now we have to compute the maximum bending moment and maximum shear force coming into the beam. So the maximum bending moment easily can be computed. You can see the structural analysis already we started in the last semester also, and this semester also. In the earlier classes we discussed how to compute the bending moment and the shear force. Okay, so shear force we denote it as a VC. So you can see, very simple. You can do it by yourself also. The earlier beam already shown that beam. If you do the structural analysis, you will get all the values for the maximum shear force and maximum bending moments. Please look into and do it in your hand, all the step-by-step procedures. So now checking for the depth. So in the step 3 already you know what is the maximum bending moment and what is the maximum shear force. So now whatever depth we have assumed in the step 1, now it's time to check whether this depth is sufficient or not. So we use our formula, beam formula, whatever we have used beam design case, or you can use SP16 also, whichever we discussed in the last class. In the column design we have used SP16, so that SP16 also can be used to find it out, what is the depth required. So again here we have to check two steps. I mean, one is obviously with the based on the shear force, whether depth is sufficient. Same beam design will follow, exactly beam design. So the same formula we have used, and for the waist slab and for the landing slab, both we have to check it. Tau v we are checking, right? Tau v means shear stress conditions we are checking, and then the bending stress also, both we are checking it. So same thing, if you recall the slab design, what we did, we used k value, right? Close number from this one, depending on the depth of the slab, k value has been chosen from table number 29. It's 456 tau c value we considered. So everything exactly same whatever we did earlier. Okay, so for the slab design. So step number 4 we checked it. Now step 5 is now determination of area of steel. So mu by bd square, if you recall in that IS 456 or the SP16 also, directly we can use or you can use our normal beam design beam formulas, whatever I discussed earlier also. So from there you can easily find out what is the percentage of steel PT, right? Mu is equal to what we used, if you recall. So you already know mu is equal to 0.87 Fy AST, right? Then d minus 0.42 xu, right? So this is the formula. From here you can easily compute what is AST. So same thing there. So here in this example I have shown using the SP16 code, table number 2. If we use from there also, directly you can find out what is the percentage of steel required, or we can use our conventional method using this formula and you can find out what is the AST required. So anything is fine. We have discussed earlier also in the beam design, so same thing will follow here also. So find out what is the percentage of steel required. So once we know percentage of steel, now you can provide it how much area is required for that. Similarly, this is for the waist slab, this is inclined slab, and landing B top portion also you have the bending moment. So same process will follow, and ultimately our design will be completed. So this is our step 5. Now step 6 is development, length, and the dimension of main bars, right? So in the for the waist slab, what dimensions we are providing. In the last slide we have seen already, we have computed percentage of steel and all. So now we provide how many bars we are providing. 12 mm diameter bar at the rate, 120 meter center center and all. How we know that? It's the same process whatever we did earlier also for the landing slab and for the waist slab also. These are the values for that. And now this is our final slide of this staircase design, is the final detailing. Now we design the slab. See, this is the landing portion 1, landing portion A, landing portion B, right? Landing slab B. So, and this is the inclined portion where the slab we have designed it. So you see all the reinforcement now we have given, main reinforcement, transverse reinforcement, even for the slab. So these two portion will be same as a slab design. If you see, we have provided the top reinforcement also, because we have the negative reinforcements, and this portion will go inside the wall. Okay, so full details of this type of slab design now we got it. So middle portion we designed it as a beam, and this two we designed it as a slab. Very simple design, and ultimately the detailed view of the slab will be prepared, and it will be given to the site engineer. So he will execute same thing on a site. So that's how actually we can design a staircase, or even in the matter any structure in the world, we can simply divide it into this beams design, column design, and the slab design, and we can do it. So today we demonstrated how we can design a staircase, and this is only we considered a simple staircase, but same thing can be done with helical staircase or circular staircase also. So in the next lecture, we'll be discussing about the foundation. So foundation is also a very much important structure element in a structure where loads are transferred to the ground. So that will be discussed in the next lecture. Thank you so much.